Far from Earth, a planet passes in front of its star and leaves a tiny wound in the light. Astronomers study that wound and realize a few wavelengths are missing. Something in the planet's atmosphere absorbed them on the way through. That is the whole beginning. Not a coastline, not a forest, not a creature moving in a sea. Only a chemical shadow carried across more than 100 light years and caught by a mirror in space. That is enough to wake up the oldest hope in science, and it is also enough to make people run ahead of the evidence. One interesting gas can begin sounding like a verdict. One plume can begin sounding like a captured sample from an alien sea. One unusual rock can begin sounding like a witness finally ready to talk. Yet planets manufacture misleading chemistry all the time, and our instruments now find exciting hints much earlier than they can settle every serious alternative. By the end of tonight, you will understand how a real proof would have to survive repetition, contamination control, and non-biological alternatives before scientists could say, under sustained scrutiny, that another world is alive. If you enjoy exploring questions like this with me, subscribing to the channel helps others find them too. Sharing the video helps even more. Let's begin. Imagine a mechanic testing whether a bridge can carry weight. The first steel beam matters, but nobody opens the road because one beam looks strong. The real question is whether the entire structure keeps its shape once wind, vibration and time begin pressing on every joint together. Proof of life works that way. A clue can be thrilling, it can even be rare, but it does not become proof until the rest of the structure keeps standing around it. NASA's ladder of life detection is useful because it slows that rush without draining the wonder out of it. The ladder asks what sort of environment was found, what signal was actually measured, what non-biological process could imitate that signal, and whether the result survives repetition under another instrument or another analysis. Those are not annoying side questions taped onto the discovery. They are the discovery. A life claim is only as strong as the hardest alternative explanation it survives. That is different from the emotional shape of most headlines, which prefer a simple upward slope from first clue to final discovery. Real progress rarely behaves that neatly. A new measurement can absolutely strengthen the case, but it can also reveal a fresh weakness, expose a hidden assumption, or show that two incompatible explanations still fit the same data. From the outside, that can feel like hesitation. Inside the work, it is often the moment when the field starts seeing the problem honestly enough to solve it. You can feel the logic in ordinary life. If a doctor suspected something serious from a single blood marker, you would not want courage from that doctor. You would want imaging, repeat sampling, a history, and an honest discussion of what else could produce the same number. That instinct is not distrust. It is the way important conclusions become durable. Life detection beyond Earth is burdened with even more weight because the claim would change more than one patient file. It would change our picture of the universe. False positives sit at the center of that burden. Oxygen can be produced by harsh atmospheric history. Methane can come from water and rock working together without any biology present. Organic compounds can arrive by meteorite, emerge through volcanic or hydrothermal chemistry, or be remade inside minerals long after any living system is gone. A plume erupting from an icy moon can reveal a real ocean and still stop short of showing any organism. The signal may be genuine while the story built on it is still wrong. There is an opposite danger too. Life can be present and still stay quiet. A biosphere may sit below a hostile surface, live at low abundance, or leave traces that are too faint, too diluted, or too easily destroyed for the first instruments to catch cleanly. That means silence is not always emptiness. A world can hide from us just as convincingly as dead chemistry can mislead us. The field has to stay sensitive enough to notice rare evidence while remaining disciplined enough not to overread it. This is why researchers like Catling and others keep returning to convergence instead of spectacle. A persuasive case needs evidence that fails in different ways rather than evidence that only seems separate on a quick reading. Two gases inferred from the same atmospheric model do not buy as much independence as they appear to buy. A texture in a rock and an isotopic pattern from the same fragment are stronger, but they can still lean on the same hidden weakness if contamination touched that material early. A plume measured during one fast fly-through can be remarkable and still rest on one geometry, one instrument suite, and one encounter. The ladder becomes clearer when you imagine how a serious case would grow over time. Perhaps a rover first shows that a once wet environment preserved carbon compounds at all. Later work might reveal that those compounds sit in a mineral setting that resists easy geological explanations. Another instrument could narrow the isotopic story. A contamination challenge could fail. A separate team could recover the same basic result while using different assumptions and methods. None of that would be decoration. Each step would remove one particular way of being wrong. That is what the ladder means in practice. It is not a classroom diagram. It is a sequence of disappointments a claim has to survive without breaking. The ladder also protects the early clues from being asked to do impossible work. A methane spike can matter in its own right. A Mars sample can matter because preserved chemistry was found at all. A distant atmosphere can matter because it shows our telescopes are finally reading real planetary compounds across interstellar distance. None of those advances has to masquerade as the final answer in order to be important. In fact, they become more meaningful once they are allowed to occupy the right run. So the first lesson here is not stay skeptical in the thin internet sense of the word. It is something harder and more useful. Stay proportional. Let an environment mean environment. Let chemistry mean chemistry. Let a candidate biosignature mean a candidate biosignature. Then ask what would have to happen next before the biological interpretation became harder to escape than to accept. Once you hear the subject that way, the whole search changes. It stops sounding like a lottery ticket waiting to win, and starts sounding like a long argument being built piece by piece. That argument is where the excitement lives. We are not short of intriguing clues. We are short of clues that survive every serious way of being wrong. The worlds that tempt us most are the worlds where that difference becomes hardest to ignore, and the first trap on that road is one of the oldest atmospheric shortcuts of all. Oxygen feels so persuasive that many people treat it as a near verdict before the real work has even begun. Oxygen is the atmospheric clue our own planet taught us to trust. Here, free oxygen survives because life keeps renewing it against chemistry that would otherwise pull it back into rocks, water, and other compounds. That background sits so deep in our intuition that even hearing the word can make another world feel closer to biology. The instinct is understandable. It is also incomplete. If a distant planet showed a strong oxygen signature, the first reaction would be perfectly reasonable. Oxygen is reactive. It does not like to remain free forever. So the natural thought is that something on that world must be replenishing it. The problem is that biology is not the only process capable of doing that. Under some conditions, starlight and planetary history can leave behind oxygen-rich air without a single living thing participating. One route is brutal rather than biological. Ultraviolet radiation can break water vapor apart high in an atmosphere. Hydrogen escapes more easily into space because it is lighter. Oxygen stays behind. Over long periods, a world can lose water, keep oxygen, and end up advertising a ghost of habitability rather than a living surface. The gas is real. The story it tells is bleak. That is why oxygen never gets to speak on its own. Researchers want to know what kind of star the planet orbits, how violent that star is in ultraviolet light, whether the world looks dry or water-rich, whether carbon monoxide is present, whether methane is present, how thick the atmosphere may be, and what broader climate picture fits the spectrum. The same oxygen signature can move toward life on one world and toward photochemical residue on another. Context does not weaken the clue. Context decides whether the clue is worth its biological tension at all. Earth is useful here mostly as a warning about analogy. Our atmosphere is not a single data point floating in space. It belongs to oceans, continents, carbon cycling, burial, volcanic recycling, and a biosphere that transformed the planet over immense time. When people imagine finding oxygen elsewhere, they often compress that whole biography into one measurement. An exoplanet spectrum does not hand over a biography, it hands over part of a silhouette. That is why biosignature work moved away from molecule worship and toward relationships among gases. Oxygen can become more persuasive when it coexists with compounds that should rapidly react away unless something keeps renewing both sides of the imbalance. Carbon monoxide can complicate the picture. Methane can complicate it in a different direction. Water history, surface pressure, cloud structure, and host star behavior all join the argument. The question becomes less like, did we find oxygen, and more like, what kind of planetary history can still support this whole pattern? There is a human-scale way to feel the difference. If you smelled smoke in one room of a building, you would care immediately, but you would still want to know where it came from, what the weather was doing, whether machinery was running, and whether someone had opened a vent nearby. Smoke is meaningful before it is decisive. Oxygen on another world belongs to that category. The clue may be important the moment it appears. The verdict still depends on the room around it. That point matters especially because many of the most accessible small exoplanets orbit red dwarfs. Those stars can spend early eras in a harsh ultraviolet mood. If a planet lost large amounts of water under that radiation, oxygen or ozone may accumulate as the leftover chemistry of atmospheric damage. In that case, the signature that first sounded hopeful begins to read like the residue of a harsher planetary past. The gas did not change. We simply learned enough history to hear it differently. Earth also teaches a subtler lesson. Free oxygen here was not present at the same level throughout our planet's history. It emerged from long interaction among microbes, geology, sunlight, and time. That means oxygen is not a biological calling card stamped automatically onto any inhabited world. It is one possible outcome of one planetary story. When we look elsewhere, we usually see the output before we know the story. That order tempts overconfidence. There is another reason oxygen needs company before it sounds persuasive. A living planet does not merely contain one dramatic gas. It maintains relationships among gases over time, while surface chemistry, sunlight, and climate keep trying to rearrange them. If a world really were breathing, in the broad planetary sense, we would expect the atmosphere to show tension rather than one isolated triumph. That is why researchers keep asking about methane, carbon monoxide, water history, and host star behavior in the same breath. They are trying to hear whether the whole atmospheric system sounds worked on, not whether one note was loud enough to excite us. There is also the possibility that a world may be biologically active and still fail the oxygen shortcut entirely. Earth itself spent a vast span of time inhabited before free oxygen reached modern abundance. A distant biosphere could remain mostly microbial, chemically quiet, or locked into environmental conditions that do not leave much oxygen in the air. That means oxygen can mislead in both directions. It can appear without life, and life can exist without producing an oxygen signal strong enough for us to notice. The gas is therefore valuable precisely because it is conditional. It tells us when a planet deserves closer atmospheric scrutiny. It does not tell us that the question has already been answered. So scientists are not downgrading oxygen when they refuse to treat it as instant proof. They are giving it its real size. Oxygen remains one of the most compelling atmospheric clues available to us. What it cannot do is close the case by itself. Once that becomes clear, the emotional burden shifts toward the next gas people hope will rescue certainty. Methane feels more flexible, more lively, and in some ways more tantalizing. That is exactly why it becomes the next recurring trap. Methane is worth getting excited about. That needs to be said plainly before the cautions pile up. On Earth, methane is deeply entangled with life. Microbes make it. Organic material releases it. It can also be destroyed quickly in some environments, which means seeing it suggests ongoing activity rather than ancient residue. So when methane appears in a planetary atmosphere, in a plume, or in a local sample, the reaction is not irrational. It is a real scientific signal that something chemically interesting is happening. The problem is that life does not own methane. Rock does some of the same work. Water moving through certain minerals can drive reactions that produce hydrogen and then methane. Heat and pressure can release methane from buried chemistry. Ancient material can break down without biology. In other words, methane can point toward metabolism, but it can also point toward geology that remains active enough to keep making reduced carbon compounds without a living source. That makes methane a recurring stress test across several worlds at once. On Mars, methane has appeared in a pattern that remains hard to explain cleanly. Around Enceladus, methane is part of a larger chemical story in the plume. In the K218b debate, methane was one of the gases that made the atmosphere feel unusually interesting in the first place. The same molecule keeps reappearing because it sits right at the edge where planetary chemistry and biological possibility both become plausible. What methane cannot do by itself is separate those roots. A lone methane detection tells you a planet or moon is worth more attention. It does not tell you why the methane is there. That question needs company. What other gases are present? How stable is the methane over time? What temperature and pressure conditions exist where it is being produced or preserved? What mineral reactions are possible? Is there a plausible non-biological source that fits the larger environment without too much strain? This is where the phrase biosignature gas can mislead. It sounds like a badge a molecule wears on its own. In reality, the badge is conditional. Methane in the right atmospheric company becomes much more interesting than methane alone. Methane in disequilibrium with gases that should quickly destroy it can be powerful. Methane in an environment where geological pathways look weak becomes more interesting still. The clue strengthens not because the molecule changes, but because alternative explanations start losing ground. Even then, caution remains part of the signal. Methane is not disqualified by ambiguity. It becomes valuable through ambiguity handled well. A strong life search does not ask whether methane was seen and then stop. It asks what kind of world could keep methane present, what other compounds should accompany each explanation, and what measurements would help kill off the weaker stories. The goal is not to worship a gas. The goal is to understand the system that keeps the gas there. There is a useful everyday picture for this. Imagine hearing footsteps above you in an old building. The sound matters. It means something happened. But footsteps can come from a person, a machine, heating pipes shifting, or old wood settling in a patterned way. If you hear laughter too, or a door open, or a chair move, the picture changes. One sound begins the question. A group of sounds reshapes the answer. Methane works like that. It is often the first noise in the ceiling, not the solved case. That is why methane deserves respect without becoming a shortcut. Underplay it, and the search loses one of its most compelling chemical clues. Overplay it, and every active planet starts looking biologically haunted. The middle position is harder but truer. Methane matters most when it survives inside a broader context that makes purely abiotic chemistry look increasingly strained. Until then, it remains one more important clue that can still tell more than one story. Mars, Enceladus, and K218b each teach a different methane lesson. On Mars, the problem is local release and unstable timing. On Enceladus, the gas sits beside hydrothermal hints and ocean chemistry. On K218b, the gas becomes entangled with atmospheric structure and retrieval models. The molecule stays central because it really does mark active chemistry. It fails to settle the case because active chemistry still covers a wider territory than life alone. Lifetime matters as much as abundance. In one atmosphere, methane may be destroyed quickly by ultraviolet radiation or oxidants, which means even a modest amount implies fresh replenishment. In another atmosphere, methane can survive more comfortably, so the same abundance says less about urgency. Scientists therefore care about how the gas sits inside the wider environment, what should destroy it, what could renew it, and which companion gases make one pathway look more plausible than another. The molecule never interprets itself, the world around it does. To understand why this keeps happening, especially for distant worlds, we need to slow down even more. Before a gas becomes a claim, before a claim becomes a paper, before a paper becomes a headline, a telescope has to measure something astonishingly indirect. That measurement itself is part of the burden of proof. Mars, Enceladus, and K218b all show different versions of methane's problem. On Mars, the issue is timing, location, and source. Around Enceladus, the issue is whether methane belongs to hydrothermal activity alone, or to something biologically richer. On K218b, the issue is how atmospheric structure changes the meaning of the gas entirely. The same molecule survives those transfers because methane is genuinely diagnostic of active chemistry. It fails to settle them because active chemistry is still broader than biology. Lifetime matters too. Methane does not persist the same way in every atmosphere. Ultraviolet light, oxidants, pressure, and atmospheric composition all change how quickly it should be destroyed. That means the same abundance can carry different implications in different places. A small amount that should vanish quickly may be more interesting than a larger amount that can linger easily. The concentration never interprets itself. The environment interprets it. There is also a strong reason researchers care about methane in company rather than solitude. If methane is being produced abiotically, what else should accompany that pathway? If it is tied to water rock reactions, what mineral or chemical environment should support that story? If it is biological, what wider disequilibrium might help it endure? A better methane case is usually a more crowded case. Not crowded with adjectives, but with constraints that begin excluding rival routes one by one. That is what a stronger methane signal would really look like, not simply more methane, repeated methane, contextual methane. Methane paired with other measurements that strain geological explanations and survive contamination concerns. Until then, the molecule remains a superb invitation and a poor verdict. And once you understand that, some of the later disagreement stops feeling surprising at all. From a distance, an exoplanet is usually not a visible world. It is an effect on light, a tiny dimming when it crosses its star, a tiny wobble in the star's motion, a tiny set of missing wavelengths when starlight filters through a narrow ring of atmosphere at the planet's edge. That last method is one of the most powerful things modern astronomy can do. It is also one of the easiest things to romanticize incorrectly. The planet does not appear as a globe with clouds and continents. A telescope like James Webb is not watching waves break on K218b or seeing microbes drift through a sea. It is reading how molecules absorb light at different wavelengths. If methane blocks some wavelengths and carbon dioxide blocks others, those patterns may be extracted from the filtered starlight. The work is real, it is extraordinary, but it is still reconstruction, not direct witnessing. That reconstruction depends on models. Scientists ask what kinds of atmospheres could produce the spectral pattern that was measured. Pressure matters, temperature matters, clouds or hazes matter, the star's own activity matters, wavelength coverage matters. If one part of the spectrum is missing, several different atmospheric structures may still fit the remaining data. That does not mean the science is unreliable. It means frontier measurements come with families of plausible interpretations rather than a single clean portrait. This is why disagreements in exoplanet atmospheric work are not scandals. They are built into the method. One group may favor a hydrogen-rich atmosphere with certain gases and cloud properties. Another may find that a different atmospheric structure or a different treatment of the data explains the same observations almost as well. A third may argue that what looked like one molecule is not statistically secure once more wavelengths are included. That is not the field failing. It is the field doing exactly what a hard question requires. Time becomes part of the evidence too. NASA has been clear about this point. Strong exoplanet atmospheric claims can take hundreds of observing hours. They often need repeated transits. They need coverage across different wavelength regions. They need independent analyses by teams using different assumptions. The public sometimes hears that as delay. In reality, it is the price of trying to infer the chemistry of a world more than 100 light-years away from slight changes in a star's light. There is a good analogy in stained glass. If you stand outside a church at dusk and only see coloured light falling onto the street, you can infer something about the window that produced it. Red panes block differently from blue ones. Thick glass differs from thin glass. But if part of the window is obscured, or if the light source changes, or if you see only one angle, your reconstruction stays provisional. An atmosphere read through transmission spectroscopy is not exactly like that, but the logic is similar. You are working backward from filtered light to an unseen structure. This is why an exoplanet can become scientifically more interesting at the same moment it becomes methodologically more fragile. Better data do not always collapse ambiguity. Sometimes they reveal more of it. They can rule out one easy story and open two harder ones. They can confirm that a gas is present while leaving the planetary environment that hosts the gas unsettled. They can sharpen the debate without ending it. That may sound disappointing until you remember what kind of measurement this is. A few decades ago, even talking seriously about the atmosphere of a temperate world so far away would have sounded speculative. Now the argument is about which of several plausible atmospheric states best fits real telescope data. That is tremendous progress. It is just progress inside inference, not beyond inference. The physical scale of the problem helps keep the humility in place. During a transit, the atmosphere contributes only a thin rim around the planet's silhouette, while the star does almost all of the shining. Researchers are reading chemistry from a very small filtered signal layered on top of instrumental noise, stellar variability, and modeling choices. That does not make the result weak. It explains why careful teams can disagree honestly about what the same spectrum permits. Clouds and hazes deepen that challenge. A hazy atmosphere can flatten features that would otherwise look distinct. Stellar spots and bright regions can distort what appears to be happening in the planetary signal. One wavelength range may make a gas look compelling, while another reveals that the same feature can be reproduced by a different atmospheric structure. More light does not only add certainty, sometimes it removes a confidence that was purchased too cheaply. With that in mind, one modern case becomes almost perfect for this question. It is not the case because it proves life. It is the case because it shows how progress and ambiguity can grow together. The physical scale of the measurement helps explain why. During a transit, the atmosphere is contributing only a thin rim around the planet's silhouette. The star is still doing almost all the shining. Researchers are trying to read chemistry from a tiny fraction of filtered light layered on top of instrumental noise, stellar behavior, and model assumptions. That is why different retrieval pipelines can be so consequential. Small choices propagate through a very delicate signal. Clouds and hazes complicate things further. A hazy atmosphere can flatten or blur spectral features. Stellar spots and bright regions can also distort what seems to be happening in the planetary signal. A world may be chemically complex and visually veiled to the instrument in ways that change which molecules look strong, which look weak, and which remain ambiguous. The telescope does not peer through a perfectly clear laboratory chamber. This is also why wavelength coverage matters so much. NIRISS, NEI-RSpec, and MIRI do not all ask the same question in the same way. One region of the spectrum may suggest a promising molecule. Another may reveal that the same feature can be modeled differently, or that a supposedly strong signal is not robust across the broader dataset. More light does not only add detail, sometimes it takes confidence away. That is a healthy outcome when the earlier confidence was too cheap. If a future exoplanet case ever becomes convincing, it will be because the atmosphere held together under all of that pressure. The signal will have survived more than one instrument, more than one wavelength region, more than one analysis, and more than one atmospheric interpretation. Until then, distant atmospheres remain astonishing precisely because they are so indirect. K218b sits right there. A distant world became chemically vivid enough to trigger global excitement, and almost every part of the excitement had to be handled with care at the same time. K2-Hendine b deserves to be taken seriously before it is taken cautiously, because the world itself is genuinely unusual. It orbits a cool red dwarf roughly 124 light-years away, weighs several times more than Earth, and sits in a temperature range that made scientists curious before James Webb ever looked at it. Webb then added something sharper: methane and carbon dioxide in a hydrogen-rich atmosphere with little ammonia. That combination did not prove anything biological, but it did make the planet scientifically vivid enough that the public story could outrun the evidence almost immediately. Dangerous here means headline-friendly. A temperate world, a hydrogen-rich atmosphere, carbon chemistry, methane. Then a possible sulfur-bearing molecule with a strong Earth association enters the conversation. That is the sort of sequence that makes the public leap almost instantly from chemistry to biology. Not because people are foolish, but because the pattern feels like the first time distant atmospheric data are starting to resemble the outer edge of a life discussion instead of a pure climate discussion. That is what made the dimethyl sulfide and dimethyl disulfide conversation so combustible. On Earth, dimethyl sulfide is strongly associated with biological activity, especially marine ecosystems. So once papers and commentary started discussing possible evidence for DMS or DMBs in K2-Hendine b's atmosphere, the emotional logic was immediate. A world already carrying methane and carbon dioxide in a potentially intriguing setting might now also carry a gas that, here, points strongly toward life. One can feel how the story wants to end, but that is where the scientific burden of proof becomes visible in real time. The sulfur signal remained possible and disputed, not settled. Some teams argued the mid-infrared data could support DMS or DMBs. Other analyses said the evidence was insufficient when broader data were considered. At the same time, competing atmospheric interpretations remained alive. A hydrogen-rich atmosphere over a possible ocean was one picture. A gas-rich mini-Neptune with no habitable surface was another. The same planet stayed exciting while refusing to become singular. This is exactly the kind of situation where the public often becomes impatient with science. If the data improved, why did certainty not improve at the same speed? Because better data can ask bigger questions before they answer them. With K2-Hendine b, the conversation shifted from "can we detect chemistry at all?" to "what kind of world produces this chemistry?" That is a much stronger scientific position than the public argument usually notices. It is also a much more dangerous place for overclaim, because the atmosphere starts to sound vivid before the planetary context is secure. It is just as important to notice what Webb did not do. The telescope did not show an ocean directly, identify an organism, or settle the deeper question of what sort of world K2-Hendine b really is. The planet may fit a more generous picture in which atmospheric clues hint at a potentially habitable environment under a hydrogen envelope. It may also fit a harsher picture in which the atmosphere belongs to a gas-rich planet without a surface setting that life as we know it could use comfortably. Webb gave the field a richer set of clues. It did not erase retrieval degeneracy, instrumental limits, or structural alternatives. That phrase, retrieval degeneracy, can sound technical enough to lose the listener. The plain idea is simpler. One measured pattern in light can still permit several atmospheric stories. Like seeing a shape in fog, you may be sure something is there without yet knowing whether it is a person, a statue, or a trick made by several objects overlapping. The better the data, the less wild the possibilities become. But several serious possibilities can remain. K2-Hendine b therefore teaches two lessons at once. First, exoplanet science has truly advanced. This is not empty hype built from nothing. A distant, temperate world is being chemically characterized in remarkable detail. Second, remarkable detail is not the same thing as proof. The case remains interesting precisely because its best biological-sounding interpretation is still under pressure from non-biological and structural alternatives that have not been eliminated. The 2023 Webb result mattered because methane and carbon dioxide in the same hydrogen-rich atmosphere with little ammonia gave researchers a more textured picture than they had before. Some scientists argued that such a combination remained compatible with a possible ocean-bearing world under a hydrogen envelope. That possibility was enough to move K2-HND-B out of generic catalogue status and into the far more dangerous zone where atmospheric context started sounding emotionally vivid. Then the sulfur debate sharpened the burden. A possible DMS or DMDS hint sounds almost decisive in ordinary conversation, because those molecules carry strong Earth associations. Inside the field, possible means exactly what it says. Statistical significance matters, agreement across wavelength regions matters, retrieval assumptions matter, competing planet structures matter. For a molecule with biological overtones, the scientific standard rises, not falls. That is why K2-HND-B is so educational. The planet shows what a biosignature era may actually feel like from the inside. It will probably not be a clean march from ignorance to revelation. It may instead be an uncomfortable period in which the data become good enough to force a life-shaped conversation while remaining incomplete enough that responsible scientists refuse to close it early. The public often hears that interval as hesitation. The science hears it as the first time the question has become concrete enough to argue over responsibly. That combination makes K2-HND-B the right opening era example and the wrong whole frame for the search. If the story stayed there, it would become a recap of one evolving dispute. The 2023 Webb result mattered because methane and carbon dioxide in the same atmosphere, with little ammonia, gave researchers a more textured picture than the field had for many comparable worlds. Some scientists argued that such a pattern remained compatible with a hydrogen-rich atmosphere over a possible water ocean. That possibility was enough to move the planet out of generic catalogue status and into the zone where atmospheric context started feeling unusually important. Then the sulfur discussion arrived and sharpened the emotional problem. A possible DMS or DMDS signature near 3.4 sigma is the sort of statement that sounds nearly decisive outside the field. Inside the field, it is much more provisional. Statistical significance matters. Cross-instrument consistency matters. Retrieval assumptions matter. The larger wavelength story matters. For an extraordinary biological suggestion, possible is not weakness in wording. It is the correct location on the ladder. Competing papers then did exactly what a healthy field should do. One line of work argued the atmospheric picture could still fit a gas-rich mini-Neptune with no habitable surface. Another argued the broader dataset did not support strong DMS or DMDS evidence. None of that erased the earlier progress. It clarified what the progress had actually earned. K2-HND-B had become a serious test case for atmospheric interpretation, not a solved case for alien life. That is the larger payoff. K2-HND-B lets us feel why a biosignature headline spreads so fast, and it lets us see why responsible science still slows the leap. Then it hands the story to a harsher environment. Mars removes the excuse of distance. We can touch Mars, drill into it, taste its air, and still fail to settle the answer cleanly. Mars seems like the place where ambiguity should begin to die. The world is close. Spacecraft land there. Rovers drive across it. Drills cut into rock. Instruments heat samples, sniff gases, and measure chemistry directly. Compared with exoplanet work, this sounds almost luxurious. No inference from a few missing wavelengths in Starlight. No decades of waiting for the right transit schedule. Just a machine on the ground, looking around with real local access. Then methane at Gale Crater complicates everything. Curiosity measured background methane levels below 1 part per billion on average. That is already a tiny number, and yet it matters because methane should not simply be ignored. On top of that quiet background, Curiosity also reported spikes, first around 7 parts per billion and later around 20. Those spikes were strong enough to demand explanation. At the same time, orbiters did not confirm an easy global methane picture. A close world produced a fragmented story rather than a clean one. That fragmentation is not just an annoyance. It tells you how much sampling conditions matter. Mars is not being measured from one stable vantage point under one permanent set of conditions. Curiosity samples local air near the ground. Orbiters measure differently and over broader geometry. Time of day may matter, season may matter, local accumulation near the surface may matter, transport through the atmosphere may matter. One instrument can be telling the truth locally while another fails to see the same story globally. This is a good place to resist a lazy reaction. Contradiction does not automatically mean error. Sometimes it means the planet is harder to sample than the neat version of the question assumed. Mars methane may arise from episodic release, local trapping, destruction pathways, measurement geometry, or some combination not yet well resolved. The exact answer remains debated. But the deeper lesson is already visible. Direct access does not remove interpretation. It changes its shape. That shift in shape is important. With an exoplanet, the burden rests heavily on indirect measurement and model choice. On Mars, the burden moves toward environment, timing, consistency, and mechanism. If methane is present, where is it coming from? Why does it appear in that pattern? Why does one data set see more than another? Can geology produce the observed behavior? Could the source be ancient rather than active? Proximity removes one layer of uncertainty and exposes several more. There is something almost humbling about that. We can place a rover on another planet and still end up asking questions that sound structurally similar to the distant world questions. What was measured? Under what conditions? What other explanations remain? What context is missing? The instruments are closer. The logic of proof barely softens. Mars also changes the emotional burden. A distant atmosphere lets the imagination stay abstract. A rover drilling into stone feels intimate. The public instinct becomes, if we are there, surely we can tell. But being there raises expectations more than it guarantees answers. The closer we get, the less patience we have for ambiguity. Science does not care about that impatience. It still requires the same thing. Explanations have to survive, so Mars does not rescue the life detection question from caution. It shows why caution survives even when the planet is physically reachable. Methane remains interesting on Mars because it reflects active chemistry worth explaining. It does not become proof because active chemistry still has more than one root. That is the same theme we saw at a distance, now played at ground level. Curiosity's methane work mattered partly because it was local. The sample analysis at Mars Suite was not guessing from afar. It was measuring air near the ground with enough sensitivity that even background levels below 1 part per billion were meaningful. When spikes appeared, they demanded explanation because the instrument was close enough for the numbers to feel intimate. That intimacy is part of why the public expected the ambiguity to vanish. Instead, the contrast with orbital non-detections forced a harder lesson. A gas can pool near the surface, disperse unevenly, appear episodically, or be sampled under very different geometries by a rover and an orbiter. The local detection is not automatically cancelled by orbital quiet, and the orbital quiet is not automatically irrelevant because the rover saw spikes. Mars keeps both datasets in play at once. Direct access narrows one uncertainty and reveals several others hiding behind it. It also reveals how much planetary context controls interpretation. Gale Crater is not all of Mars. A local spike near the surface may tell you something vivid about one place and one moment, while saying much less about the whole planet. That is frustrating if you want a planetary answer quickly, but it is scientifically healthy. A world is allowed to be locally interesting before it becomes globally legible. Mars keeps teaching that distinction every time one promising clue refuses to spread neatly across the entire map. Once the air stays unsettled, the temptation shifts to rock. If methane can flicker and evade easy interpretation, maybe preserved carbon in ancient mudstone gets us closer. Curiosity's methane work matters partly because the instrument itself was on the ground. The sample analysis at Mars Suite was not guessing from afar. It was heating, separating, and measuring local material. The tunable laser spectrometer could track tiny methane concentrations with enough sensitivity to make sub-parts per billion background levels meaningful. That is why the spikes attracted so much attention. They were not vague rumors in the data. They were local measurements sharp enough to demand explanation. At the same time, the contrast with orbital non-detections from the trace gas orbiter kept the story from becoming comfortable. A gas can pool near the surface, disperse quickly, appear episodically, or behave in ways that broad orbital scans miss. That leaves the field in an awkward but honest position. The local detection is not automatically cancelled by the orbital quiet. The orbital quiet is not automatically irrelevant because the rover saw spikes. The real world forces both datasets to remain in play. There is a simple scale analogy here. Sampling a valley floor and sampling the whole sky above the valley are not the same act, even if both are called methane measurements. A pocket of gas near the ground can matter intensely to one instrument and barely register to another. Mars keeps teaching that point. Proximity does not flatten the environment. It reveals how much the environment shapes every conclusion. This is why Mars functions so well as a proof standard world. It gives us access, hardware, and real samples, then reminds us that access is only one part of interpretation. Methane remains interesting because it keeps insisting the planet is chemically alive in some sense. It remains non-decisive because the path from chemistry to biology still branches too widely. Mars does contain organics, that matters, but it matters in a way that still refuses to collapse into life. Picture a Martian lake bed that has been dry for billions of years. Fine mud settled there when water still lingered on the surface. The mud hardened into stone. Radiation, burial, cracking, and time all worked on it afterward. Then a rover arrives, drills into that rock, heats a powdered sample, and finds organic carbon. The scene feels almost too perfect. Ancient water, preserved chemistry, a once habitable setting. If Mars ever had a chance to leave a chemical memory, surely this is the kind of place where we would hope to meet it. Curiosity's results at Yellowknife Bay deserve exactly that level of attention. They tell us Mars preserved carbon chemistry in mudstones from an ancient lake environment. That matters because the planet did not erase every delicate trace. Ancient environments on Mars can still be read in part, even after billions of years of damage. The search, therefore, has real material to work with rather than a purely hypothetical target. But the word organic carries more emotional weight than scientific specificity. In ordinary conversation, it can sound as though biology has already entered the room. In chemistry, the word is broader. Carbon compounds can be built by life, delivered by meteorites, generated through volcanic or hydrothermal processes, or rearranged inside rock without any organism participating. The finding opens a branch of explanations. It does not close one. NASA has been careful about that distinction because it changes the whole meaning of the result. Curiosity did not prove life. It showed preserved organic chemistry that is already a serious planetary finding. It tells us carbon-based compounds can survive in ancient Martian sediments, and it tells us some environments were gentle enough to protect those compounds from complete destruction. What it does not tell us is whether life, geology, meteorite delivery, or several processes together wrote the chemistry now being sampled. The next instinct is to ask for isotopes, and that instinct is reasonable. Biological and non-biological chemistry do not always sort carbon in the same way. Isotopic ratios can therefore help narrow the field. Yet the Curiosity isotope story did not suddenly convert ambiguity into biology. Plausible abiotic ranges stayed alive. The tool became sharper. The verdict did not arrive. Once again, better evidence created a better defined question rather than an instant conclusion. That is an important scientific mood to learn. Mars organics moved the conversation from "is there preserved carbon chemistry here at all?" toward which histories can still account for this preserved carbon. That is progress. The environment is ancient, irradiated and incomplete. A good result inside such a setting may reveal how many stories remain possible before it reveals which one wins. There is also a portability problem. A weak clue can travel from one narrative to another without much resistance. The same carbon detection can be inserted into a life story, a meteorite delivery story, a volcanic story, or a prebiotic chemistry story with only minor edits. When that happens, the evidence is telling you something honest about its current strength. It is real, but it is not yet trapped inside one interpretation strongly enough to force a biological reading. Think about a stain on paper found in an old archive. The stain matters. It proves a mark exists. But until you know whether it came from ink, oil, a fingerprint, or water carrying dissolved material across the page, the mark belongs to several histories at once. Mars organics behave like that. The page is real. The mark is real. The author is still uncertain. Yellowknife Bay makes the problem more vivid because the setting is genuinely generous. Curiosity was not drilling random rubble. It was sampling mudstones from an ancient lakebed where fine sediments could preserve chemistry more gently than harsher terrain might. That increases the scientific value of the result. At the same time, the long interval between the original environment and the modern measurement leaves plenty of room for alteration. Burial can change a rock, exposure can change it again, radiation can damage chemistry over immense time. Later fluids can move through cracks and rewrite part of the story. That long history is why multiple origins remain alive together. Carbon compounds can arrive from space. They can be produced or reshaped by hydrothermal and volcanic systems. They can be altered by rock-water reactions after the original environment disappears. A biologically produced molecule and an abiotically produced molecule can both be reduced to carbon-bearing fragments in a powdered sample unless the broader geological setting helps separate them. Perseverance has already shown how careful later missions must remain. A rock like Sheava Falls may carry textures or chemical associations that deserve intensive future work. Calling those potential biosignatures is not timid language, it is exact language. The object may be important enough to cache, revisit, and challenge from several angles while still remaining far from a demonstrated biological claim. That is why carbon chemistry has to grow into context instead of leaping over it. One promising rock is encouraging. A pattern repeating across related samples in a preserved environment with mineral setting, isotopes, contamination control, and geological history all reinforcing one another would be dramatically stronger. At that point, the rock itself stops carrying the whole burden. The place it came from begins carrying it with the rock. And once that happens, the next issue becomes unavoidable. If sample meaning depends on history so heavily, then cleanliness and custody stop being side rules. They enter the claim itself. This is also why organics remain exciting even when they refuse to prove life. They tell us where to spend future effort. A cached sample rich in preserved carbon chemistry is more valuable than a random sample that tells us little about habitability or preservation. Organics can therefore guide the search without ending it. They can mark where ancient environments were gentle enough to keep memory in the rock, and that alone is a major strategic gain for later missions and later laboratories. A sample tube is one of the most seductive objects in planetary science. It is small, it is physical, it promises intimacy. A distant atmosphere can feel abstract. A sealed core of rock feels like an answer waiting to be opened. That is why high-interest samples from Mars or future ocean world material are so easy to over-dramatize. The object looks decisive long before its meaning is secure. Perseverance has already shown why that danger matters. When a sample or outcrop is described as carrying potential biosignatures, the phrase is scientifically careful and emotionally explosive at the same time. Potential biosignatures means the material deserves attention. It does not mean the sample is a nearly solved crime scene. Preservation history matters. Mineral environment matters. Radiation exposure matters. What part of the surrounding terrain the sample came from matters. A remarkable core is still part of a geological neighborhood. That neighborhood is what turns drama into interpretation. A sample lifted out of place too quickly becomes narratively strong and scientifically weak. If a feature in the rock looks promising, scientists want to know what sits above it, below it, beside it, and elsewhere in the same formation. Was this a stable watery environment or a transient chemical pocket? Did the minerals form in a way that preserves delicate patterns well, or in a way that easily fabricates misleading textures? Does the same signal repeat across related samples, or does it disappear when the context broadens? This is why sampling strategy becomes part of the evidence itself. A planet is not settled by one trophy specimen. Ignacio and colleagues made that logic painfully clear in a different direction when they argued that demonstrating lifelessness on Mars would require large numbers of samples, perhaps many hundreds, rather than a few quiet null results. The same logic applies in a softer way to positive claims. Sparse sampling weakens both confidence and restraint. A small net catches dramatic stories too easily. Imagine trying to describe an entire forest after seeing one branch pressed through a window. The branch matters. It tells you something real. It may even be unusual enough to change your sense of the forest. But you would still want to know what the trunks look like, what other branches nearby look like, what the soil is like, whether the branch came from a healthy tree or a dead one, whether the shape repeats deeper inside. A sample is often like that branch. The object is real. The system around it decides what it means. Mars makes this painfully obvious because the planet gives us objects strong enough to tempt overclaim and contexts thin enough to punish it. One core may preserve intriguing chemistry, another may sit in a different radiation history. A third may tell you the first was local rather than broad. Geological interpretation keeps widening the frame until the sample belongs to a place, not just a headline. There is a useful emotional correction here. Dramatic samples are not bad evidence. They are incomplete evidence. They begin strong cases when they are paired with strong surroundings, repeated patterns, and good comparative logic. They mislead when they are asked to carry a planetary question alone. That lesson also travels beyond Mars. It applies to plume particles, drill cores, and any future returned sample. A specimen does not become powerful because it is vivid. It becomes powerful because its context survives pressure. Perseverance's sample cache makes that lesson practical rather than abstract. The rover is not wandering at random looking for one magical specimen. It is building a set of cores tied to a broader geological story in Jezero crater, where delta deposits, altered rocks, and ancient environmental transitions all matter. A single dramatic sample can attract attention, but the cache gains meaning because the samples relate to one another and to the terrain they came from. There is a slower statistical point here as well. Sparse sampling flatters outliers. If you only hold a few specimens, the strangest one can dominate your imagination. Once the sample set grows, the first surprise either becomes part of a pattern or shrinks into local peculiarity. Both outcomes are valuable. They are impossible if the mission is asked to settle a planetary question with a trophy object and a dramatic sentence. Geologists often work backward from place to object, not the other way around. They want the layer, the neighboring minerals, the fracture history, the burial history, and the chemistry of the surrounding unit before they trust a dramatic feature too much. That instinct can feel anticlimactic when a sample looks visually decisive. In life detection, it is essential. A pattern that looks persuasive in isolation can become ordinary once the neighborhood is known, or become much stronger once the neighborhood repeats it. Sparse sampling creates its own illusion of certainty. A few points on a map can look like a trend if there are not enough empty spaces between them. The same is true for positive clues. One striking sample can dominate attention because the comparison set is still too small. Add more samples, more related layers, more neighboring environments, and the first sample becomes either more convincing or more ordinary. Both outcomes are valuable. Neither is possible without the broader net. There is even a human-scale analogy for this. A biopsy does not mean much without knowing where it was taken, what the surrounding tissue looked like, and whether nearby samples resemble it. One dramatic slide on its own can mislead the entire picture. Planetary samples ask for the same humility. The object matters. The map around the object decides how far the interpretation can travel. That is why contamination stops sounding like a side issue the moment sample context becomes central. If samples owe their meaning to environment and history, then anything that muddies that history enters the claim itself. That shift from specimen to setting also changes what counts as a successful mission. A rover that returns many ordinary but well-placed samples may do more for the life question than one rover that finds a single dramatic object with weak context. Geological boringness can become scientific gold if it tells you how widespread an environment was, how stable it remained, and whether an exciting sample belongs to a larger pattern or only to itself. The life detection question therefore stops being where is the most spectacular clue, and becomes which sample set would survive pressure when the whole landscape is taken into account. A sealed tube can look reassuring. Metal walls, sterile hardware, barriers, gloves, clean rooms. The whole scene gives off a procedural seriousness that is easy to file under safety or bureaucracy. But in life detection, cleanliness is not just an administrative preference. It is part of the evidence. If a bold claim rests on a sample, the chain around the sample becomes part of what the sample says. NASA's planetary protection rules make that brutally clear. A mission that might search directly for life on Mars does not just need capable instruments. It needs stricter sterilization, stricter handling, and stricter protection against recontamination of hardware and samples. Those requirements are not there because the paperwork grew too large. They are there because Earth carries biology everywhere. If Earth material rides along invisibly, it can haunt the interpretation later. This changes how we should picture a possible biosignature. It is not just chemistry in isolation, it is chemistry plus history. Where was the sample before collection? What touched it during collection? What sat near it during storage? Was the hardware clean enough? Was the sealing process trustworthy? If the sample returns to Earth, was containment preserved throughout transit and curation? A spectacular molecular pattern with a sloppy history is weaker than a less dramatic pattern with airtight provenance. Restricted Earth return makes that logic even more visible. Mars sample return planning, for example, treats containment as a full mission-spanning discipline. The concern is not only whether something dangerous could be brought home. The concern is also whether the sample can still be scientifically trusted when it arrives. If the material might matter for life detection, then every breach, every uncertain transfer, every ambiguous contact point becomes a wound in the argument. There is a reason the language becomes severe. BSL-4 style containment sounds theatrical only until you understand the size of the claim. If a returned sample could, in principle, bear on alien biology, then Earth biology must be kept out of the story as aggressively as possible. The more extraordinary the possible conclusion, the less room there is for loose provenance. Think of a fingerprint on a glass. The print may be perfect, the ridge detail may be clear, but if you do not know whose glass it was, who handled it, whether it was cleaned, or when it was moved, the print weakens. The evidence did not change. The chain around it changed. Provenance works the same way in planetary science. The sample is not floating free from its history. Its history is welded to the claim. That matters for more than returned samples. It matters for landers, drills, and plume collection too. If an instrument detects organics, sulfur compounds, or other compelling chemistry, the question immediately expands. Could terrestrial contamination make this pattern? Could spacecraft outgassing matter? Could sample processing have altered the chemistry? Could a trace from Earth survive long enough to mimic something indigenous? Strong life detection logic treats those questions as scientific, not ceremonial. This can feel deflating at the beginning. The cleaner the rules become, the harder the finish line seems to get. But there is a positive side. Contamination control is not the enemy of discovery. It is what makes discovery durable. Planetary protection has two directions. Forward contamination asks what we carry to another world. Back contamination asks what we bring back, and how we contain it. In public conversation, the second direction often dominates because it sounds dramatic. The first direction is just as important scientifically. If a spacecraft seeds a site with terrestrial organics or microbes, then even a genuine local clue can become tangled with what the mission itself introduced. That is why sterilization and handling rules can become stricter precisely where the science becomes more valuable. The better the site looks for life detection, the less room there is for casual contamination. A technically weaker but cleaner result may be more persuasive than a richer result gathered with weaker controls. Evidence does not become strong by being abundant alone. It becomes strong when its origin remains legible. This is why witness materials, blanks, and custody records matter even though they rarely make headlines. If a drill bit carries trace organics from an earlier operation, if sample handling leaves an undocumented exposure, or if a return container has an uncertain seal history, then the contamination story stops being hypothetical. It enters the evidence in the same way a suspicious fingerprint enters a court case. The field does not get to wave it away after the exciting chemistry arrives. The burden becomes even clearer when you imagine a future return sample being challenged by several labs. Every powerful new assay increases the value of clean provenance, because each assay can only be as trustworthy as the sample's history. In that sense, contamination control is part of instrument design, part of mission design, and part of interpretation all at once. It is not a bureaucratic fence around the science. It is one of the beams holding the science up. Future plume capture and drilling missions will face the same logic in different forms. A fast fly-through risks one kind of ambiguity. A drill risks another. Sample processing on board risks another. Each step between world and measurement creates possible places where the story can bend away from the source. Strong mission design tries to narrow those bends before the data ever arrive. Without that narrowing, even a true signal can remain trapped in doubt. With it, a quieter signal can become stronger because fewer alternate stories remain. That is why contamination enters the claim so early and stays there. It also explains why chemically rich ocean worlds can remain thrilling without becoming verdicts. So contamination does not arrive at the end of the argument like a legal disclaimer. It enters at the moment a clue starts to look biologically interesting. The better the clue gets, the more contamination matters. That is why chemically rich ocean worlds can remain so exciting without becoming verdicts. Their samples may be accessible in a way Mars rock is not, but the same burden persists. Enceladus is the clearest example. If you wanted to design a world that keeps scientists awake without letting them say too much, Enceladus would be hard to beat. It is small, bright, ice-covered, and unexpectedly generous. Cassini found water vapor and ice grains erupting from fractures near the South Pole. Inside that plume, instruments identified salts, organics, methane, ammonia, silica, molecular hydrogen, and later even phosphorus-related chemistry. A hidden ocean started to sound more than possible. It started to sound chemically active in ways that brush right up against life's requirements. The phrase free samples became popular for a reason. Unlike an ocean locked beneath kilometers of crust with no access point, Enceladus appeared to be throwing part of its internal chemistry into space. That made the moon look almost unfairly favorable. No drilling mission was needed just to encounter material from the subsurface. The ocean, or at least material shaped by it, seemed to be visiting the spacecraft. That generosity is real science, not cinematic exaggeration. Molecular hydrogen suggests water rock reactions at the seafloor could be active. Silica points toward hydrothermal processes. Organics and salts show the ocean is not chemically empty. Methane adds more intrigue. In terms of habitability, Enceladus is one of the strongest environments we know beyond Earth. It offers liquid water, complex chemistry, and plausible energy gradients in the same hidden system. And still, none of that is a verdict. Cassini was not built as a definitive life detection mission. Its fly-throughs were fast. One of the deepest plume dives passed through material at roughly 49 kilometers altitude, and about 8.5 kilometers per second. That is astonishing access, but it is not the same as a dedicated, slow, clean, highly specific biological assay. Some molecules can share masses. Some complex species are hard to distinguish cleanly. Context about exact source regions remains limited. The chemistry is rich. The interpretive ceiling remained lower than the public imagination wanted. This is a perfect example of why habitability and proof have to stay separate. Enceladus may host one of the most compelling habitable environments in the solar system. It may even host processes that, on Earth, would make us think seriously about biological possibilities. But a chemically generous ocean is still not a demonstrated biosphere. Rich chemistry narrows the field. It does not finish the argument. Cassini therefore occupies a strangely beautiful scientific position. It showed enough to make the Moon feel alive in the chemical sense of activity and disequilibrium. It did not show enough to let scientists responsibly say life had been found. That gap is not a flaw in the mission. It is the real tension in the search. The closer a world comes to looking biologically promising, the more precisely we have to ask what was really measured and what remained beyond reach. One way to hear that clearly is to notice what the strongest Enceladus statements actually sound like. They sound like this place has ingredients, this place has energy, this place has access to liquid water, this place shows signs of hydrothermal interaction. Those are major findings. They make the Moon scientifically vivid. They also remain one rung below the claim most people care about most. If wonder takes over too early here, the whole burden of proof frame collapses. Enceladus becomes an almost discovery tale instead of a chemistry and context tale. The better route is calmer and stronger. Enceladus proves that even a world pouring intriguing material into space can stop short of a biological conclusion. Accessibility helps. It does not eliminate alternatives or instrument limits. The plume itself may not be chemically uniform either. Material from different fractures or different moments in the plume's activity may not represent the subsurface in exactly the same way. A single fly-through samples one encounter under one geometry at one speed. That can be immensely valuable and still leave the internal environment only partly constrained. A future mission would want repeat access, cleaner separation of complex compounds, and a design aimed at discriminating pathways rather than merely enlarging the catalogue of interesting chemistry. That is why Cassini's success should be heard correctly. It did not almost finish the job. It made the job far more serious. By showing water, salts, organics, molecular hydrogen, silica, methane, and later phosphorus-related chemistry in the same system, the mission raised Enceladus from speculation to one of the strongest habitable environments we know outside Earth. Raising a world to that rung is a major scientific achievement, even when the next rung still refuses to arrive. That matters because another icy moon is already moving into the public conversation with its own promise and its own danger. Europa sounds like life hunt territory in casual speech. Enceladus earns that attention partly because the south polar fractures are not just cracks in ice. They are pathways through which interior chemistry reaches space. Cassini turned those tiger stripes into a working natural experiment. Material from below was reaching an instrument without a drill. Few places in the solar system offer that kind of scientific generosity. It is one reason the Moon keeps returning to astrobiology conversations. The hydrogen and silica results matter for the same reason. Molecular hydrogen suggests water-rock interactions that can provide chemical energy. Silica particles point toward hydrothermal activity at the seafloor. On Earth, settings like that can support rich microbial ecosystems. On Enceladus, the same measurements tell us the ocean may be active and chemically interesting in ways life could exploit. They do not tell us that life is exploiting them. Instrument geometry keeps the caution alive. A fly-through at kilometers per second samples a changing plume under limited control. Some molecules fragment, some signatures overlap. Some environmental context remains indirect because the spacecraft is not lingering inside the ocean itself or performing every imaginable assay. That is why Cassini almost found life is the wrong sentence. Cassini found a world worth taking much more seriously as a habitat candidate. A stronger future plume case would need more than richer chemistry. It would need repeat sampling, higher specificity, tighter control over contamination, and measurements that distinguish biological and abiotic pathways, rather than merely registering more of the same excitement. NASA's own language is more disciplined than casual speech, and learning to hear that discipline correctly may be one of the most useful filters in the whole subject. Europa Clipper already tells us something important before it reaches Jupiter. Its mission language is narrow on purpose. The spacecraft launched in October 2024 and is set for arrival in 2030, but it is not framed as the mission that will reveal alien organisms hiding beneath the ice. Its stated job is to evaluate Europa's habitability, the properties of the ice shell, the ocean beneath, the chemistry, the energy environment, and the conditions that might support life. That can sound like a smaller ambition than the public hoped for. In reality, it is a major scientific question in its own right. Habitability asks whether a world has the ingredients and physical conditions needed for lifelike systems to exist. That includes water, chemistry, energy sources, transport between regions, and environmental stability over time. A mission that sharpens those answers can transform the map of where deeper life search efforts should go next. The difficulty is that public language often treats habitability as a soft synonym for inhabited. It is not. A world can be habitable and empty. A world can have an ocean, useful chemistry, and energy gradients without hosting biology. The difference matters because once those two words blur together, every serious mission to a promising moon begins sounding like a delayed confirmation story. Europa is exactly where that blur becomes dangerous. The moon almost dares the imagination to run ahead. Ice shell, global ocean, tidal heating, chemistry that may exchange between seafloor, ocean, and surface. Possible plume activity, though not yet secured in a way that removes doubt. All of it sounds like the setting of a biological reveal. But a mission built to study habitability is not underperforming if it refuses that reveal. It is honoring the logic of the question. There is even a kind of scientific maturity in that restraint. If Europa Clipper tells us more clearly where the chemistry is richest, how thick the ice may be, how material may move between ocean and surface, and where future instruments should focus, that is not a consolation prize. It is exactly how a strong life search program should behave. Better questions before louder claims. This is why phrasing matters so much. Suitable for life is not a coy way of saying probably alive. It means what it says. Conditions suitable for life are conditions. They are not inhabitants. Hearing that difference clearly protects the public from two opposite mistakes. One is hype, where every habitability result is inflated into a near discovery. The other is cynicism, where a mission sounds disappointing unless it delivers a biological headline. Europa helps us understand the proof burden because it forces the mind to separate potential from demonstration. A planet or moon can move much closer to the zone where life seems plausible and still remain outside the zone where life is evidenced. That gap is the whole subject in compact form. So better worlds are not enough. Better access is not enough. Better ingredients are not enough. The next improvement has to come from instruments that separate more sharply, and from missions designed to ask discriminating questions instead of merely collecting impressive chemistry. Europa Clipper embodies that narrower discipline in hardware as well as language. Radar can help constrain the ice shell. Spectrometers can map surface composition. Fields and particles measurements can refine the understanding of Europa's environment. Gravity and magnetic clues can sharpen what we infer about the ocean beneath. None of those tools is a direct biological detector. Together they are designed to improve the physical map on which later biological questions would stand or fail. Plumes make the public imagination race here too. Reports of possible water plumes above Europa have been intriguing for years, but they have not settled into a simple repeated access story the way casual retellings often imply. That uncertainty matters because mission plans built around a dramatic access point change if the access point is intermittent, weak, or absent. Habitability work has to stay robust, even if the most cinematic route never appears on command. The positive point is that habitability is not a consolation prize. Learning how thick the ice may be, how surface materials relate to the interior, and how chemically promising the ocean environment looks would change the entire strategic map of life search missions. It would tell us whether Europa deserves deeper, riskier, and more specific biological tests later. That is exactly how careful exploration should proceed. Europa also forces patience because its most cinematic access route remains uncertain. Possible plume detections have been reported, but they have not settled into a reliable picture of repeated sampling opportunities. That means the Moon cannot simply borrow Enceladus's free sample narrative. Mission design has to remain valuable even if no plume appears on command. In practical terms, that keeps the emphasis on building a physical map first, rather than writing a discovery story before the hardware arrives. And that map matters personally for how we imagine the Moon. If you picture trying to judge a sealed ocean from orbit, every extra clue about ice thickness, chemical exchange, and internal structure changes what later missions could dare to ask. Habitability, therefore, is not a soft preface to the real work. It is the work that decides whether the real work can be done responsibly at all. The mission's restraint is a kind of honesty we may need more of in the next decade. Europa Clipper can transform the life debate without ever claiming to detect life, because it can tell us whether the Moon's most promising stories survive contact with better physics. If the ice shell proves more hostile, if material exchange looks weaker than hoped, or if the chemistry points in a less generous direction, that is valuable knowledge too. A strong search does not only gather encouraging signs, it also learns which dreams were based on scenery rather than evidence. In that sense, Europa teaches a discipline of listening. When an agency says habitability, it is not hiding a discovery behind timid phrasing. It is naming the rung it is actually trying to reach. Hearing that rung correctly helps future headlines make more sense and keeps the search from being distorted by promises the mission never made. It is natural to think the bottleneck is sensitivity. If we could just see fainter signals, separate smaller compounds, detect more molecules, or image more precisely, perhaps the life question would finally give way. Sensitivity matters, but life detection does not usually fail because nothing interesting was measured. It often fails because several interesting explanations survive at once. Better instruments help most when they separate those explanations. Cassini shows the point nicely. Flying through Enceladus's plume at high speed was an extraordinary achievement. Yet some molecular species remained hard to distinguish cleanly because instruments have finite specificity. Similar masses can blur together. Complex mixtures can hide inside broader categories. A future instrument that tells apart lookalikes more cleanly may do something more important than simply detect more material. It may kill off an abiotic or non-diagnostic interpretation that currently survives. The same logic applies to exoplanets. More wavelength coverage is not just more data, it is a way to test whether one atmospheric model still holds when new spectral regions are included. Higher resolution is not just a prettier spectrum, it is pressure applied to the alternatives. The best technological advance is often the one that turns a broad family of plausible stories into a narrower family. But better instruments can still waste themselves on weak questions. A mission can gather richer chemistry and remain trapped in ambiguity if the observations are not designed to distinguish living and non-living pathways. That is why the proof ladder matters upstream before the data arrive. What alternative explanations are being targeted? What measurements would specifically reduce confusion instead of merely increasing wonder? Which compounds, structures, or isotopic patterns would actually tighten the case rather than decorate it? This is where specificity starts outranking spectacle. A quieter measurement that eliminates a serious abiotic route may be scientifically stronger than a dramatic new detection that leaves all the old alternatives standing. That can make real progress look less cinematic than people expect. The breakthrough may not be the first time a world becomes chemically interesting. It may be the moment one ambiguity quietly dies. There is a broader lesson in that. Technology does not substitute for theory or for disciplined question design. The field does not simply need stronger eyes. It needs sharper reasons for looking where it looks, and clearer criteria for what would count as a genuine shift in explanation. Otherwise, the instruments get more powerful while the public story stays trapped in the same loop. Intriguing clue, rapid excitement, slower retreat into ambiguity. Seen this way, better questions are almost a kind of instrument themselves. They filter the evidence before the hardware touches it. They ask not, what can we find, but what would this finding eliminate? They ask whether a proposed observation moves us from general chemical richness toward discriminating evidence. They ask whether a future result would be portable across many stories, or whether it would begin to trap the explanation in one narrowing corridor. It helps to separate clarity from sensitivity. A louder signal is not automatically a clearer one. A blurrier photograph can contain more light and still tell you less than a sharper image with less drama. Instruments work in a similar way. A stronger detection can still leave a crucial ambiguity intact if it does not distinguish between molecules, structures, or pathways that overlap in the measurement. This is why mass spectrometers, chromatographs, and spectrographs become valuable in different ways. One may separate same mass species that were tangled together before. Another may broaden wavelength coverage enough to expose a fragile atmospheric model. Another may test an isotopic pattern that geology struggles to mimic. The useful question never changes. Which alternative explanation gets weaker if this measurement comes out a certain way? That is why the strongest future lane is not just a better flyby or a sharper spectrum. It is a situation where many kinds of tests can be applied to the same material again and again by different methods and different labs. That is what returned samples promise when everything around them goes right. Not certainty by magic, pressure by abundance. This is also where mission design becomes moral in a scientific sense. Time on a spacecraft is expensive. Sample mass is limited. Every observational window has opportunity cost. If a mission spends those scarce resources collecting prettier ambiguity instead of more discriminating evidence, it may still generate headlines while leaving the central question in almost the same place. Better questions protect against that waste. They force the field to spend its sharpest tools on measurements that can actually remove rivals, rather than merely decorate them. It helps to separate clarity from sensitivity. A blurrier photo with more light is still blurry. A sharper photo with less dramatic lighting may tell you more. Instruments behave in a similar way. A stronger signal can still leave crucial ambiguity if it does not distinguish between candidates that overlap in mass, wavelength, or chemical outcome. Life detection often needs that sharper separation more than it needs a louder overall measurement. Mass spectrometers, chromatographs, and spectrographs become powerful not because they generate scientific awe by themselves, but because each can eliminate a different family of excuses when used well. One tool may separate same mass molecules that were previously tangled together. Another may broaden wavelength coverage enough to expose a weak model. Another may test an isotopic pattern that geology struggles to match. The key question is always the same. Which alternative story dies if this measurement comes out a certain way? Good question design also protects the field from false negatives. If scientists ask only the easiest biological question, they may miss subtler forms of life or subtler traces. If they ask only the broadest chemical question, they may gather beautiful ambiguity and little else. The most useful missions split the difference. They stay open enough to notice something real and sharp enough to discriminate among the strongest rival explanations. That is why improvement in this field may feel intellectually satisfying before it feels dramatic. A stronger instrument is valuable when it turns a conversation from "interesting chemistry exists" to "this specific non-biological route no longer works." Once that happens a few times in the same case, the whole argument changes shape. A returned sample changes the argument because it changes the room in which the argument happens. A rover or flyby always works inside tight limits of power, mass, time, and instrument choice. So when the spacecraft leaves, much of the immediate opportunity leaves with it. Bring the material home, and the object enters a different scientific life. It can be stored, divided, revisited, challenged, and compared across years instead of minutes, which means it stops being a brief encounter and becomes a standing problem the wider scientific community can keep pressing from new angles. That matters because life detection is rarely answered by one clean look. A grain, filament, or pocket of carbon has to survive several different kinds of questioning. One team may ask whether the structure is really part of the rock or only a crack lined with later chemistry. Another may ask whether the carbon isotopes lean away from easy geological explanations. A third may care most about how the organics sit inside the mineral matrix and whether they cluster in a way simple contamination would struggle to copy. Those questions do not all use the same tools, and they do not all leave the sample unchanged afterward. That is one reason returned material changes the standard so dramatically. Some tests consume the material, others demand elaborate preparation, and some only become persuasive when a later method can challenge them from a different angle. A rover cannot carry a whole university with it, but a laboratory on Earth can bring many specialties to the same grain of dust or flake of rock. The puzzle does not become easy. What changes is the depth of the cross-examination the object can survive. Repetition becomes a different kind of strength there. If related subsamples keep telling a compatible story under different methods, alternatives begin losing room to breathe. A geological explanation that survives one assay may strain under a second. A contamination idea may sound plausible until custody records, isotopes, and spatial distribution all begin disagreeing with it. Returned material makes convergence more than a list of clues. It makes convergence something that can be tested repeatedly from different angles. That is why returned samples are often imagined as the strongest future lane. The imagination, though, still needs discipline. A sample brought home is not an automatic witness for biology. It may represent the wrong environment. It may be too altered. The chemistry may still be portable across several explanations. Contamination may still shadow the whole chain. A better laboratory cannot rescue weak provenance. In some ways it raises the stakes, because a bigger claim is now being tested under brighter light. The custody problem therefore comes back with greater force. If a sample is going to be cut apart, chemically scrutinized, isotopically mapped, and challenged by many teams, then the path it took to the laboratory has to be trusted with equal seriousness. Every uncertain transfer, every compromised seal, every poorly documented contact point becomes more dangerous as analytical power rises. Stronger testing cannot heal weak history. Still, when everything goes right, returned material offers something almost nothing else offers. The same object can sit still while the questions around it become sharper, moving from texture to isotopes to preparation controls over a span of years, without disappearing from the argument. That long availability matters because the goal is not to wait for one spectacular assay that ends the debate. The goal is to watch weak explanations begin cracking in several different places at once, while the sample itself remains available for the next challenge and for the next generation of instruments. There is a simple human analogy for that. Hearing one witness once can give you a clue. Bringing that witness into many rooms under different lights, with different questioners and different records, tells you whether the account survives pressure. Returned samples behave like that. They do not promise a confession. They promise a harsher interview than a spacecraft can usually conduct on site. Earth laboratories also widen the menu in a more literal sense. A suspicious texture does not have to remain a single photograph from one instrument. It can be checked under another imaging method, then compared with the chemistry in the rock immediately around it. A curious organic signal does not have to remain one blended average either. Scientists can ask whether it appears everywhere, only in one layer, only beside one mineral, or only in fragments that passed through a particular preparation step. Even destructive analysis starts sounding less alarming in that setting, because opening the sample can reveal relationships a remote instrument would never see from the outside. Returned samples change the social structure of evidence as well. Different labs can challenge one another. Different preparation methods can expose preparation artifacts. Blind intercomparisons become possible. A surprising pattern that appears in only one instrument or one lab is fragile. The same pattern surviving across several teams becomes much harder to wave away. Extraordinary claims should not depend on extraordinary trust in one group, and returned material gives the field a chance to prove that. This is also where the positive standard can finally be named without fantasy. Proof would not look like one magical molecule or one thrilling core placed on a table and recognized at a glance. It would look like a sample or a family of samples surviving a long series of attacks. Every time a non-biological or contamination-based explanation tried to absorb the result, some other line of evidence would keep the biological reading alive. The material would become harder to reinterpret cheaply. That is what makes returned samples such a powerful future route, not because they shortcut the burden of proof, but because they give the burden many more ways to act. They let the same claim be stressed again and again until what remains is no longer the most exciting explanation, but the most durable one. And once that durability becomes the target, the search can stop asking which single clue sounds strongest and start asking what a real proof standard would actually feel like. Returned samples also change what counts as failure. A spacecraft that misses one crucial assay may never get another chance. A sample on Earth can keep yielding answers even after an early interpretation proves wrong. An ambiguous result no longer has to end as disappointment. It can become a signpost telling the next lab where the chemistry was mixed together too crudely, where the contamination controls need to be stricter, or which tiny region of the material deserves a more careful cut. That longer laboratory life matters because proof is rarely linear. A strong case may need to survive false starts, corrections, and years of scrutiny before it sounds durable. Returned material gives the field time to do that without the object vanishing back into space. It also lets future instruments enter the story. A sample collected in one technological era can be questioned again in another, and that matters because the first convincing signs of alien life may hide in details our current tools only partially resolve. There is something else a returned sample can do that remote sensing almost never can. It can be argued over physically. Different teams can request subsamples. Laboratories can preserve part of the material for future instruments that do not yet exist. An interpretation that looks persuasive in one decade can be revisited in the next with a better technique and a sharper question. That long horizon matters because alien life evidence may not come in one generation-sized package. A sample might first be valued for geology, then for chemistry, then much later for a subtle pattern nobody knew how to test when the material first arrived. Returning the sample gives the future a vote, and that vote may be essential when the claim is as large as life beyond Earth. By this point, the answer should sound less like a headline and more like a construction. Proof of life beyond Earth would not arrive because one clue became emotionally irresistible. It would arrive because several independent lines of evidence kept pointing toward biology after the strongest non-biological explanations were pushed hard and failed to hold. For an exoplanet, that would probably mean an atmospheric case built slowly, repeated detections across wavelengths, independent instruments, gas combinations that remain difficult to sustain abiotically under the planet's star and climate conditions, models of the world that stop supporting the easier non-life stories. Perhaps not absolute zero uncertainty, because frontier science rarely grants that, but enough convergence that biology begins to explain the full pattern more naturally than its rivals do. For a nearby world, such as Mars or an ocean moon, the stack would look different but no less demanding. Chemistry would matter, but so would structure. Isotopes might matter, but only inside strong geological context. Samples would need clean provenance. Signals would need repetition across sites or subsamples. Independent teams would need to attack the material from different angles and keep finding that the non-biological routes strain more than the biological one does. This is why the best universal definition of proof is not a checklist with sacred boxes. It is a relationship among explanations. Biology becomes the hardest exit. Every other route keeps losing support. Geology no longer accounts for the full chemistry. Photochemistry no longer fits the atmospheric context. Contamination no longer survives the custody chain. Instrument artifact no longer survives replication. What remains is not one miracle clue. What remains is one explanation that keeps taking weight without collapsing. There is a bridge analogy that fits here better than almost anything else. You do not prove a bridge by admiring its design from a distance. You load it, you stress it, you look for the parts that bend first. You try to find the hidden weakness. A proof-level life detection claim would behave the same way. Scientists would keep loading the argument with alternate explanations, with new tests, with new data, with competing models. The case would strengthen because it kept surviving the strain. That is also why the first real proof may feel less cinematic than people imagine. The public often expects a dramatic single moment. More likely, the field would go through a period where resistance slowly thins. A second dataset supports the first. A contamination concern falls away. A geological pathway looks less plausible. An isotopic pattern stays stubborn. A laboratory replication holds. A rival model weakens. At some point, the honest sentence changes from "this is an exciting clue" to "biology is now the strongest surviving explanation." That shift may be quieter than the headlines that came before it. Quiet does not mean weak, it means earned, and it gives us the most useful tool in this whole subject. When the next claim arrives, the right question is not whether the clue sounds lifelike. The right question is what other explanations remain alive after the clue is placed inside context, measurement limits, contamination control, and repetition. A claim grows strong not because it is vivid, but because escape routes keep closing. That standard also protects wonder from hype. It lets us stay excited about a strange atmosphere, a Martian sample, a methane spike, or an ocean world plume, without pretending the answer is already in hand. Curiosity no longer depends on premature certainty. The search becomes more satisfying, not less, because each clue has a real place in a larger structure. There is also a social side to convergence. The first persuasive case will not only survive chemistry and geology, it will survive the culture of science itself, including rival teams, independent reanalyses, skeptical papers, instrument cross-checks, and years of people trying to prove the claim too large. That is healthy. A conclusion about life beyond Earth should have to survive a field full of smart doubters before it is allowed to settle. In that sense, proof will feel less like revelation and more like resistance draining away over time. An abiotic path that once looked viable will stop fitting the data as new measurements arrive. A contamination concern will weaken once custody records and repeat tests refuse to support it. A later method may land on the same answer without leaning on the same hidden assumptions as the first. The field will not stop arguing. It will simply have fewer strong exits left open. There is a personal scale version of this as well. If you were following the story closely, what would change first would not be your emotions. It would be the shape of the objections. Early on, every clue can be answered with a broad alternative. Later on, the alternatives begin shrinking. They require more special pleading, more hidden conditions, more coincidences, or more contamination than the biological reading requires. That shift is subtle, but it is where a field starts recognizing that one explanation is carrying the evidence more naturally than the rest. That is often the first moment a careful observer can feel the ground move, even before the largest public language changes with it. Proof would also have to survive time. A claim that looks strong for 1 month and then weakens under better calibration, broader sampling, or another team's reanalysis is not proof. A claim that stays strong after months or years of hostile checking begins to move into another category. That is why the first confirmed case may look slower than many people want. Time is not the enemy of a real discovery. Time is one of the tests it has to pass. So yes, we really could prove life exists on another planet, but the proof would almost certainly come as convergence. One reason the life question stays hard is that absence speaks poorly. A planet can fail to produce a dramatic biosignature for many reasons besides lifelessness. Life may be sparse, it may live underground, it may use chemistry that leaves only weak atmospheric traces. The environment may destroy those traces faster than they accumulate. Our instruments may ask the wrong question or sample the wrong place. Silence is therefore a dangerous thing to overinterpret. Mars is the easiest place to feel that problem because the planet invites a simple test it cannot deliver. People imagine driving to the right rock, drilling once, and learning whether the world ever hosted biology. Real environments do not cooperate so neatly. Ancient lake beds differ from volcanic plains. Radiation-exposed surfaces differ from buried sediments. One sample may come from a place where chemistry was preserved. The next may come from a place where preservation was poor, even if life once existed nearby. A quiet sample in the wrong spot can look final when it is only local. That is why researchers such as Ignacio and colleagues can argue that proving lifelessness on Mars would demand enormous sampling depth. The point is not that Mars is secretly alive unless disproved. The point is that a negative answer has its own burden of proof. If biology could hide in pockets, in subsurface environments, or in rare ancient deposits, then a few null results do not close the map. They tell you where life was not obvious under one set of conditions at one moment of measurement. Ocean worlds make the same lesson even sharper. Europa and Enceladus may contain vast internal oceans, but most of those oceans are inaccessible to us. Even if plume sampling or surface chemistry turns up nothing conclusive, that result has to be heard against the fact that we are sampling an indirect pathway into a hidden environment. A plume may not carry the relevant molecules efficiently. A surface deposit may have been altered. The most biologically active part of the ocean may not communicate cleanly with the place we measured. Silence in a difficult geometry is not the same thing as silence in a fully open laboratory. Exoplanets are harsher still. A distant world might host a biosphere that leaves no atmospheric signal strong enough for present instruments to recover. Perhaps the life is buried under an ice shell, perhaps the chemistry is mild, perhaps the atmosphere is thick with haze that erases the diagnostic clues we most want to hear. Perhaps the host star complicates the spectrum so severely that a subtle biosignature gets lost in retrieval noise. A null result there can mean little more than this. If life exists, it is not announcing itself in the narrow way our current method can hear. That does not make negative results useless. It gives them the right shape. A quiet atmosphere can still rule out the loudest stories people wanted to tell about a planet. A non-detection can show that certain gases are not pouring into space in obvious abundance. Sterile-looking samples can reveal that one environment was chemically poor, badly preserved, or simply less promising than the map first suggested. Those are real scientific gains because they narrow the question honestly. What they usually do not do is settle the entire existence problem by themselves. There is a useful human analogy in medical screening again. A negative test can be deeply reassuring when it targets the right thing with enough sensitivity in the right conditions. The same negative test can be ambiguous when the disease is patchy, early, hidden, or poorly matched to the method. Life detection on other worlds lies much closer to that second situation. We are often screening uneven, ancient, or inaccessible environments with imperfect access and incomplete models. Negative findings matter. They are simply not the final word as often as people wish. This is also why good mission design has to plan for ignorance rather than only for discovery. A rover, orbiter, or flyby should be able to say more than, "We did not find the exciting thing." It should help explain whether the problem was the environment, the preservation, the sampling geometry, the instrument sensitivity, or the biological assumption itself. In other words, a strong null result is diagnostic. It teaches the next mission where the blind spot was. The deeper lesson is that proof of absence can be as demanding as proof of presence. To say with confidence that a world is lifeless, scientists would need broad sampling, repeated access, and a strong understanding of where life could plausibly hide or fail to register. That is a far taller order than a headline usually admits. It is one reason the search for life will probably advance through narrowing and ranking long before it advances through absolute yes or no declarations. So silence should make us more careful, not less curious. Sometimes the lesson is that we aimed at the wrong layer of rock. Sometimes it is that a favored biosignature was far too blunt for the chemistry we were testing. Sometimes the result mainly reveals the limits of our instruments, our sampling path, or our assumptions about where life would leave its clearest mark. What silence cannot always do is end the question. The universe may contain life that speaks softly, or locally, or in chemistry we are only beginning to frame correctly. In that sense, the absence of a dramatic clue is often information about our method as much as it is information about the world we were trying to hear. There is a practical reason to keep that distinction sharp. If a mission returns only a flat answer, people are tempted to say the world itself was silent. But a method can fail quietly too. A drill may never reach the better preserved layer. A plume pass may miss the denser chemistry by timing alone. An exoplanet spectrum may wash out because clouds, haze, or stellar noise blurred the very feature we hoped would stand up. The difference between world silence and method silence is the difference between closing a case and redesigning the next question. That is why a careful null result can still change the field in a lasting way. If a Mars sample shows that certain sediments destroy organics quickly after exposure, the next mission may stop chasing the same exposed layers and start prioritizing protected cores. If a plume analysis suggests the ejected material has been heavily altered on the way out, engineers may rethink when and how often they fly through it. If an exoplanet atmosphere keeps hiding behind haze, telescope time may shift toward worlds where the geometry gives cleaner leverage. A negative answer is not empty when it teaches us where the map was misleading and where the next measurement gains the most honesty. There is also a quieter benefit that matters over long stretches of research. Rich null results keep a field from wasting years on the wrong confidence. They can show that a cherished shortcut has failed under real conditions, that one environment preserves clues badly no matter how appealing it looks in pictures, or that a famous biosignature becomes unconvincing once background chemistry is measured properly. That kind of result can feel emotionally flat in the moment because it does not give the satisfying yes many people want. But it prevents a deeper disappointment later by keeping the search attached to reality instead of to hope. Mars offers the clearest picture of that discipline. If repeated drilling in one class of terrain keeps producing weak or degraded chemistry, that does not mean the whole planet has been judged. It means that terrain class has taught us something about preservation and exposure. The same logic would matter at Europa, Enceladus, or a distant exoplanet. A strong null answer narrows where the better question lives. In a subject where access is scarce and every measurement is expensive, that kind of narrowing is not a consolation prize. It is one of the main ways honest progress happens. It also keeps the field from chasing the same mistake under a new headline. That is why negative results should be designed to be rich rather than empty. A good null finding says more than nothing happened. It explains what environment was tested, what class of biosignature was targeted, how sensitive the measurement truly was, and which future paths now look wiser or less promising. In a field where life can hide, a rich null result becomes a map correction. It may close one door, but it often opens a more informed one somewhere else. And that is often exactly the kind of progress the search needs. And that brings us to the final practical question. Suppose one day the evidence does start surviving all this pressure. Suppose the field begins to lose its easy exits. What would that discovery actually look like in public time, in scientific time, and in the slow transfer between the two? The public often imagines discovery as a single day marked by a press conference and one dramatic sentence that flips history on its hinge. The first credible proof of life beyond Earth will probably feel slower than that. There may be an early paper that ignites the story, but the real change will come afterward. Other teams will reprocess the data. Critics will sharpen competing explanations. New observations will be demanded, not because the first result was worthless, but because the claim is too large to settle after one strong week. The argument will keep moving until one interpretation begins surviving every new attempt to weaken it. That slow arrival is not a flaw in science. It is the part that makes the conclusion trustworthy. A result that matters this much should pass through skeptical hands before it settles. Rival laboratories should be able to test a returned sample. Independent analysts should be able to run the same exoplanet spectra through different retrieval pipelines. Instrument teams should have to show that a signal is not an artifact of calibration, noise treatment, or unmodeled stellar behavior. If the claim is real, every one of those attacks becomes an opportunity for it to strengthen. History gives us small versions of that rhythm even outside astrobiology. Important scientific conclusions often begin as unsettling suggestions and only later become obvious in retrospect. The first measurements rarely carry all the authority the mature case will carry. Confidence grows because repetition strips away the easy objections. At the end, people remember the discovery date. What really changed the field was the long period in which alternatives stopped working. For a distant atmosphere, that may mean one observing program hints at a pattern, another wavelength region supports it, a third reduces a competing atmospheric model, and a later analysis shows the host star is less able to mimic the result than critics feared. For a nearby sample, it may mean one lab sees an intriguing signature, a second lab reproduces it with another preparation method, a third confirms the isotopic tension, and a fourth shows that contamination does not explain the pattern. No single step needs to look cinematic. Their combined effect is what makes retreat harder. There will also be long stretches in which the public hears uncertainty as weakness, while scientists hear it as honesty. That mismatch is built into the subject. A responsible team may spend years describing a result as possible, promising, or provisional because those are the truest available words. Commentators outside the field may hear those words and assume the signal has collapsed. Then, quietly, the same cautious language may harden over time as the case keeps surviving new tests. Discovery may therefore feel emotionally anticlimactic even while becoming scientifically overwhelming. This matters because media logic tends to reward novelty over durability. The first hint of a biosignature may receive more attention than the fifth careful follow-up that actually makes the case stronger. But for the question we are asking, durability is the real event. If biology beyond Earth is ever shown convincingly, the most important change may be a boring one. The language of the field will stop sounding like protective caution and start sounding like ordinary description. What was once the bold interpretation will become the baseline one. There is another reason the discovery will arrive slowly. Even after the existence question stabilizes, the meaning questions will explode. What kind of life is it? How old is it? Is it related only by chemistry or by deeper principles we recognize from Earth? Does it sit at the surface, under ice, in rocks, or in an atmosphere? Was the biosignature direct, indirect, ancient, or active? A proof of life is not the end of interpretation. It is the beginning of a new, much larger interpretation. That later phase may be emotionally strange for everyone watching. The public will want the first answer to feel total, as if the main mystery has finally been closed. Scientists will know the opposite. The moment a case becomes persuasive enough to count as proof, it also becomes large enough to split apart into harder questions. Is the biology active now, or ancient? Does it live in one narrow niche or across a whole environment? Are we seeing familiar chemistry doing unfamiliar work, or something more distant from Earth's history than we expected? Proof would not simplify the universe. It would make the universe more detailed than it was the day before. That is why a future discovery should not be imagined as a trumpet blast followed by silence. It should be imagined as a long argument changing shape. The claim begins as controversial, Then the strongest objections slowly narrow, replication accumulates, and the people most eager to disprove the result stop finding easy ways to do it. Eventually the burden flips. In the early phase, the biological reading feels too bold. Later, the non-biological reading begins to sound strained. That is the moment the center of gravity moves. If you were living through that shift, the most reliable sign might be surprisingly ordinary. Scientists would stop spending all their time defending the claim's right to exist and start asking what its consequences are. Missions would be designed around details rather than around first confirmation. Review papers would stop centering on whether the case is serious and start centering on what it implies. That is what mature discovery looks like. It becomes infrastructure for the next question. So the first proof of life on another world may not look like revelation descending from the sky. It may look like patience being rewarded as a difficult signal survives, a difficult sample keeps holding up, and one hard explanation slowly outlasts every simpler rival. By the time the public feels the full weight of the answer, the science may already have been living with that answer for a while. That slow arrival should not make the prospect smaller, it should make it feel heavier. A conclusion like this would have been earned the hardest way available to us, through repetition, resistance, and time. Not by wanting it, not by fearing it, not by one clue sounding dramatic enough to silence caution, by the much rarer event of many independent pressures finally leaning in the same direction at once. And that pace may be the clearest sign that the case is real. Fast headlines can be manufactured by novelty, by ambiguity, or by wishful reading. Slow confidence is harder to fake. It grows when instruments disagree less over time, when contamination worries fail to reproduce, when rival models start needing special pleading, and when the same broad answer keeps returning under different assumptions. If alien life is ever confirmed, the most astonishing part may be how ordinary the final transition feels inside the literature. 1 month, the conclusion is still treated as daring. A year later, it is the default backdrop for the next round of questions. An exoplanet case would likely mature slowly. First a gas or pattern becomes intriguing, then another wavelength region supports it, then the host star's behavior looks less able to mimic it, then an abiotic pathway starts looking physically strained. Then an independent team recovers the same basic story with different assumptions. None of those steps alone would be the finish line. Together they would make retreat from the biological interpretation harder each time. A local case would build differently. Repeated samples from related environments would matter. Clean handling would matter. Isotopes, organics, mineral setting, and perhaps fine-scale structures would all need to align without leaning on one hidden weakness. One line of evidence might first open the door. Several others would have to walk through it and still find the same room on the other side. That means proof is not zero doubt. It is durable preference under pressure. The field would still argue about details, timelines, and implications. What would change is the center of gravity. Biology would stop sounding like the boldest interpretation and start sounding like the most robust one left standing. That standard also protects wonder from hype. It lets us stay excited about a strange atmosphere, a Martian sample, a methane spike, or an ocean world plume, without pretending the answer is already in hand. Curiosity no longer depends on premature certainty. The search becomes more satisfying, not less, because each clue has a real place in a larger structure. So yes, we really could prove life exists on another planet. The proof would come when chemistry, environment, custody, and independent confirmation stopped fighting one another and started telling the same story. Not perfectly, not magically, just strongly enough that biology became harder to escape than to accept. It is worth returning to the objects that tempted us most. A few dark lines missing from Starlight, a breath of methane in thin Martian air, carbon locked in ancient mudstone, a plume from an ocean hidden under ice, a sealed sample tube waiting to be opened under clean light. None of those things deserves mockery. Each one is exactly the kind of clue a real search for life should care about. The mistake is not excitement. The mistake is stopping at excitement. A molecule can matter and still mislead. A sample can be dramatic and still portable across several explanations. A habitable environment can be chemically rich and still remain uninhabited. Even the best instrument can produce a real signal that supports more than one world behind it. That is why the burden of proof has to stay cross-world and layered. Atmospheres need context. Rocks need surroundings. Samples need history. Plumes need specificity. Every clue needs a contamination test, an abiotic test, a measurement test, and, eventually, an independent confirmation that does not simply echo the first result. The subject is not one spectacular discovery waiting in hiding. It is a series of partial clues being forced to survive harder and harder questions. If the first credible proof ever comes, it will probably feel different from the tease cycle that trained most of us. It may not begin as a thunderclap. It may begin as resistance draining away. A non-biological route fails. Then another. Then another. A second instrument agrees. A third kind of test points the same way. A clean chain of custody holds. The chemistry stops looking portable. The context stops looking forgiving. The biological interpretation stops sounding like the bold guess and starts sounding like the one explanation left standing after the rest have been pushed out. That is the standard worth carrying forward. Not did someone find one exciting sign, but what was measured, what else could make it, what context surrounds it, how clean is the evidence, and which explanation keeps surviving pressure. Once you start hearing alien life headlines that way, the story changes. They stop being emotional yes or no events. They become checkpoints in a longer argument. And that longer argument is not weaker for being slower. It is stronger because it refuses easy miracles. Somewhere beyond Earth, life may exist in air, under ice, inside rock, or in forms we are not yet asking about correctly. We do not know. What we do know is the shape a responsible answer would have to take. Not one clue, not one molecule, not one world carrying the whole burden alone. That is also why a strict proof standard should not make us numb. It should make us better at noticing which clues are truly moving the field. A new atmosphere can matter because it narrows possibilities. A new plume result can matter because it sharpens chemistry. A returned sample can matter because it opens a deeper gauntlet. Each step can be exciting without pretending to be the last. If you were holding the next big alien life headline in your hand, the useful question would not be whether it sounds dramatic enough. The useful question would be whether the claim has begun to lose its easy exits. Has geology been pressed hard enough? Has atmospheric context narrowed enough? Has contamination been handled cleanly enough? Has another team, another instrument, or another kind of test kept the same answer alive? Once those questions begin receiving strong answers together, the field will not need a theatrical moment to know something changed. The first proof will begin when biology becomes the hardest explanation to escape.